for an extended period of time. This causes dopant ions to diffuse into the substrate in all directions and recreates the nearly perfect crystal structure of the silicon lattice. The N-well is where the P-channel transistor will be built. More advanced processes also create P-wells where the N-channel transistors are built. Shallower wells may also be implanted within the deep wells to provide a dopant gradation. In our simplified transistor, the thin layer of silicon dioxide damaged by implantation is etched and regrown. An insulation layer of silicon nitride is then deposited. Photolithography again exposes the transistor regions, and a plasma etch process removes the silicon nitride not covered by the photoresist. In a furnace, a thick insulating layer of silicon dioxide is then grown to reduce the electric fields between the surface and the underlying regions. More advanced processes create substrate trenches, then grow oxide liners on the sidewalls, which is followed by an oxide deposit that is etched back. Shallow trench isolation, along with high-energy implantation, are eliminating the need for extended thermal diffusion. The wafers are then prepared for the next implant, which adjusts the threshold voltage. The difference between the gate voltage and the threshold voltage determines current flow across a transistor's channel. To create these regions with uniform electrical characteristics, a medium current implanter with DC acceleration is used. Here, the wafers are implanted individually to ensure maximum control of the ion dose. Boron trifluoride gas is delivered to the source chamber, along with non-toxic gases such as argon. By applying 40,000 volts across this white insulator, positive ions created in the arc chamber are extracted from the source region and accelerated towards the mass-analyzing magnet. This magnet bends the beam, so only the desired boron ions pass through the apertures. From the right side of the implanter, we see the scanning mechanism and acceleration column. A varying voltage applied to scanning electrodes running at 976 Hz causes the elliptical beam to scan very quickly from left to right. A parallelizing lens corrects the beam so it heads straight towards the wafer throughout the scan. A second drop of 64,000 volts accelerates the beam further. The largest drop in voltage occurs at the end of the acceleration column, where up to 150,000 volts provide the ions with their final energy and speed. In the next station, the speeding ions enter the angular energy filter. Here, in the process chamber, the beam is bent by 15 degrees to remove contaminants. Only the ions with the correct energies and angle go through the slits. A setup flag blocks the slit as it monitors the beam current. A beam profiler moves into the path and measures the beam's uniformity. When the system is ready for implant, the flag opens and the accelerated ions begin to bombard the wafer. A mechanical system creates a uniform scan by moving the wafers up and down. Normally, the beam is invisible to the naked eye. When we change certain conditions to make the beam visible, it appears stationary. In fact, it's actually scanning from left to right at about 1,000 cycles per second. The thin oxide layer damaged by implantation is removed, and a new layer is regrown. The first conductive layer to be deposited is polysilicon. Photolithography and plasma etch define the gate electrodes of the CMOS transistors. These gates will turn the transistors on and off. The side edges of the gates will also become the masking edge for the implantation of the source and drain. Today's chips are faster than ever, and designers achieve this speed by shortening channel lengths. This, however, causes electric fields around the drain to become so large they create reliability problems. To correct this, a lightly doped drain gradient is created near the gate. One way to begin this gradient is with a halo implant, which increases the number of dopants just beneath the gate. This requires tilting the wafer to approximately a 45-degree angle. As larger, heavier species, indium and antimony are often used in these high-tilt implants. Since they don't travel as far within the crystal, they can be placed more precisely. As solid sources, they are loaded into small heaters beside the arc chamber and vaporized during implantation. This high-tilt implant of indium will create an extension tip of P-type material. This will help keep the shorter channel regions separated. The lightly doped drain region is then created using a low-energy, high-current implanter. As with the high-energy implanter, this system also uses mechanical scanning. From the other side, we can see the front of the process chamber. Here, the wafers are loaded onto the large disc, which will move horizontally and rotate at high speeds during implantation. Arcing gas is injected into the arc chamber and ionized. The extraction voltage shoots positive ions towards the more negative region. Then the beam enters the